this very important notion that I roughly formalized in the last lecture or so of principal bundle. And let's say alpha be an action of G. I mean a right action, so on the right action, which is free. Let's have these two words to make sure we understand these words, free and proper. Two important words. Of course, without saying P is a manifold. So you start with an action of a P group on a manifold. Free and proper. Two very important conditions. Let me show you the picture you must have of that. Here's the upstairs space. And here's the downstairs space, which is the quotient P modulo G, which we'll call M. This is a quotient space. So this is the orbit space. So over every point here, we have the fiber over x. So this projection we'll call pi always. And pi, so pi inverse of x is the fiber over x. This is the quotient, and when we take a point in the fiber, P, then if P is a point in the fiber, then G of P is the fiber. That's the definition of this quotient. Equivalence relation is the space of fibers. And that's the equivalence relation. We have that throughout mathematics, in algebra, geometry, and in analysis. There we go. Now, in general, this is a horrible thing. In general, the quotient by a group action on a space is a terrible thing. However, upstairs is a manifold. The action is implicitly action by different morphisms. It is free and proper. If you have such an action, what anybody in the world does is he puts transversally to the fiber, so of complementary dimension, what we call a local section. So a local section. We talked about that also when we were talking about Maria's local section and other vibration. Yes?
I was wondering, how do you know that GP is well defined? What if I take another P in the fiber, in the pre-image of X? Would it still be the equivalence class of...
So, you mean we can take another P like here
Yes.
in the same fiber?
How do I know it's going to give us the same orbit?
fibers by definition are orbits. So, you know, the fiber is an orbit, so it's the same orbit. So you're asking, yeah. So her question, I'm going to start writing MQ, Maria question. Yeah, and the Alan answer. You have say F equals G of P. Okay, that's the fiber. And you take P hat in this orbit. Some other P. I think you're asking about that, right? Then Alan says G of P hat also equals that. Okay, because it's an orbit. You just check it. You write down what the fact is. Write down the fact that P hat is equal to G of P for some G, and then fool around it and you just see it's tricky. It's really, but you have to check. I'm glad you asked. Okay. Secondly, this is a manifold. It is a manifold of a certain codimension. So it is obvious that we have a complementary local. This manifold may be running around some terrible way, but if we take complementary sections small enough, it will not intersect this manifold. It's this picture, right? Yeah. And then this is a differentiable slice. This is something like a disk or something. And this is isomorphic. And this is the big step by this projection to a neighborhood of the base. This is the big step. Right? It means that if you take a fiber nearby here, it intersects it in one point. You take a fiber nearby here, it intersects an orbit. Nearby here, it intersects in one point. And of course, this gives you a collection of points down here. Right? So this is a map which identifies this section with this. And this gives the differentiable structure on the base. So this is a differentiable slice. And this gives the differentiable structure on the base. Now you ask, maybe, did I exaggerate? Did I lie a little bit? Am I Donald Trump? So he lies all the time. I do not lie. I try to tell the truth, even in mathematics. Yeah. There is a big hammer here that we have used. And the hammer here is that. If this action is not proper, the orbits, first of all, may not be closed. They are closed, and therefore we have a good quotient topology. Right? Secondly, you may have a horrible phenomena that the quotient space is not even Hausdorff. You understand that? Otherwise, the quotient space may not even be Hausdorff. You see, the usual thing that you can make very easily with R actions is two fibers, but one fiber closes up to two other fibers, something like this. And so if you take a slice here, really you're slicing here. So you see, you cannot separate those two things. You get it? You cannot separate, if the picture is really like that, you cannot separate the 2 points on the quotient. So the danger is, so the Bourbaki symbol here is in general, quotients of this type, without the properness assumption, may not be Hausdorff. There are many dangers, but this is one of the main dangers. You may not be able to separate points in the quotient topology. So this is called a principal bundle. It is a bundle because it's locally trivial. You see, it is a product of the section and the fibers, so it's a bundle. And it's easy to check all all discussions of what a bundle is.
Okay. So by alpha, do you really mean pi, or is it another map?
Where
Let G be a Lie group and alpha be a Lie group.
let G be a Lie group, which acts by alpha. This is the letter alpha, maybe it's not.
Yeah.
On a manifold P. Right out.
So this is not the projection map, it's something else.
Pi is the quotient map.
Yeah.
So, okay, an equivalence class of a point P is the orbit of P. Is a set. But you can think of pi of P being the equivalence class in P modulo the equivalence relation. Okay, does that answer?
Yeah.
Okay. This is the prototype setup of everything in life, right? You have a group. This group acts in a good way, free, and I insist on proper because I need something topological. And we have a quotient. The quotient is a manifold. The fiber. And here comes the big mistake. Here comes the big mistake. Everything I said is right here, but here, and people will say, and the fiber is a group. The fiber is not the group. Given a point, you can identify the fiber with the group, which is the orbit. But the identification depends on the point. You get it? Yeah. So, yeah, she's...
So the principal bundle is the group itself, or is it the group with the action, or what is it?
The principal bundle is written on the board. It is a space P with the G action, which is free and proper, basta. However, the bundle, in the classical sense of bundles, is the quotient of the space P by the group action. Each fiber is an orbit of the group. It acts freely, so you can identify. There's no question about it. Given a point, I can identify that orbit with the group. But the identification depends on the point. Yeah? So it is not, yes, you see what I'm saying? The fiber is not a group. The fiber is an orbit of a group, which you can identify with the group. Okay? That's the principal bundle. This is a rather new concept in mathematics, a rather obvious concept. The first person who really understand how to use this, in my mind, in mathematics, explicitly, that I learned about this. In Strasbourg, people were students of Cartan. And this is an example of a student of Cartan who really knew geometry and groups. So I don't know if he defined this or not, probably not, but he certainly understood how to use it. Okay, I think I can't explain that much better. Okay. So the main example that I beat into your head is the P is equal to Cn plus 1 minus 0. It's upstairs. And here we have the projection on the Pn. See, that projection is pi, and the fiber is, the group here is C star. And the group action is G acts on Cn plus 1 minus 0 by the action alpha. And you just, what do you do here? G, let me just say G of a vector here of a point Z in these coordinates is, and let's just say G times G, Z where G is in C star. Very lucky. This is a C star principal bundle. Okay. Okay. Now, the fundamental thing that we all need to learn in mathematics, in my mind, is the fundamental question. We talked about with Maria, we talked about everybody here, the question how to push down objects from upstairs, the principal bundle space, to downstairs. This is really one of the fundamental questions in mathematics. You have some space, and the interesting space is defined downstairs, and you want to know how to push things down. Okay? So this is a really interesting question. And here, we're interested in pushing down differential forms. The idea was we want to get a Kähler form on the base. We're looking for what I call the Fubini-Studi form, and I'm going to push down a form from upstairs to define the form downstairs. We talked about it several times. Maybe you're getting bored with this discussion, but I think it's an important discussion. So we make two remarks. Remark one. Let's call it, again, this mapping. So, pardon me. We will do this. I'll answer this question in the general statement. So we have a principal bundle, which is a principal G bundle over N with structure group G. We call this the structure group of the principal bundle. Okay? So this is an easy exercise. What you do, you assume you push something down and see what it means. Okay? So take omega on the base.
Sorry.
Yeah.
So earlier you said that P is the manifold.
Yes.
Okay, so now you have a map from the manifold M, which is
Another map.
So P is the fiber here, or?
No, the P is the total space upstairs. The fibers are.
Okay, so P is the fiber on M, whereas are we trying to push it down to M?
Given a form up here, we want to push it down here to M. Yes? So to answer the question, I go the other way around. I take a form on M and pull it back and see what condition it satisfies. Okay? Isn't that reasonable? I do. Okay? So take a form on M and study the pullback of omega on P. Right? You cannot believe that all forms can be pushed down. Right? They do crazy things at different points of the fibers, they do all sorts of stuff. You cannot believe that. So you take a form downstairs and pull it back and see what it satisfies. Okay? It satisfies two conditions. One, it's completely obvious. The pullback is G invariant. Right? Right. So you can check that very easily because, well, just check that it's invariant because it's the pullback. It doesn't do, nothing happens along the fiber. And secondly, this is the main condition. For any, maybe I'll draw the picture again. let's see here. So I'll just say it though, for any tangent vector VP tangent to the fiber, so the notation I'm going to tangent at P to the fiber through P. So maybe I'm going to call this X, where Fx, no, I'll call it Fp. Fp is the fiber at P, which is P inverse, pi inverse of pi of P. So for any such point, so we take here a tangent vector in the fiber direction. Right? We take a phi tangent vector to the fiber. What does it mean pullback? Pullback says, say on a vector like that, pullback says push it forward and apply it. Right? But if you push it forward, you get the zero vector. So for any such tangent vector tangent to the fiber, it follows that the contraction of that vector Vp with the pullback form is zero. Is zero. Right? You put it in because it's good, that form has to kill it. So those are two obvious conditions. Okay? If you have a form downstairs, you pull it back, and those are two obvious conditions. So the theorem, which you can prove very easily, is just a proposition, but useful proposition, which you can check easily to check if you've understood these. I'm going to give you a remark that will help. Is that if so mu a form mu on P is the pullback pi star of omega if and only if the conditions are satisfied. 1 and 2 are satisfied. Okay? And now I'm going to sketch the proof for you, but you will immediately believe this. Okay? Is this. And this is the idea that Maria had it last time. Maria was saying, well, we just say some vectors down there and push them up there and do things. And she's right about it in this case. And here's the point. I'm going to draw the picture again. Here's N. Here's the fiber over M and P. And here are a bunch of forms. Well, it's a K form. So it's a K form here. Yes, V1 through VK, let's say, but let's just draw an arrow just for fun, right? It's a K form, so we have but K arrows downstairs. We can handle it, K arrows. And what Maria's idea was just to lift this thing. So this is V, and we lift it, and let's call this, I don't care. We just have lambdas around. Okay, lambda of V. Now you agree I can do that because this tangent map is surjective. This is the entire point of mathematics. You have a surjective map, then you have something in the pre-image. Yeah, but the trouble is you have many things in the pre-image, right? You have many things in the pre-image. So you have lambda one lifting of this thing, and you have another lifting of this thing. I hope I drew it nicely. 2 liftings of this thing in the pre-image. Right? Yeah? That's the problem. Because what you would like to do is you would like to define you want to define mu of b, v. I'm just going to write down, this is what I learned from physics people. Be very optimistic, just write it down. And most of the time it'll work if you're lucky. So, mu of v, you want to write down as a definition, would be omega of lambda 1 of v. Now, that's a whole chain of vectors. That's a K form, okay? And now, this is the problem with your idea. Lambda 1 of v and lambda 2 of v are different. And so, you ask the question, is this the same thing as lambda 2 of v? Right? If it's not the same thing as lambda 2 of v, you're in major trouble, right? I mean, you agree with me. If it's not the same, right? However, what about lambda 1 of v minus lambda 2 of v? Now, yeah?
Isn't mu the form upstairs and omega form downstairs?
This is absolutely right. This is what I'm doing. Let's go through the logic again to make sure. Apparently, I didn't explain nicely. So we want to push a form downstairs. So I want to create a form mu downstairs. How am I going to create it? I'm going to create it by taking a vector here downstairs and telling you, or a vector or a chain of vectors, or k vectors. I have to tell you how I apply mu to that. Right? Mu is supposed to be the push down of some form upstairs. So if I have some form upstairs that I'm trying to make push down, okay, I lift this thing and I have two lifts.
But you wrote on form mu on p.
Of course, you're absolutely right. So this is mu on p. Yeah, yes. This is correct. This is correct. But I changed. Yeah, I changed. Yes. Okay. So is the pullback of omega? So mu on p. I think I've exchanged mu and omega in this discussion. That's what I've done, right? Let's try it. So I have omega downstairs, and I want to say a form upstairs is going to be a pullback of a form downstairs, mu, and okay. I have to define mu of, what we need is then mu okay. Terribly sorry. Have I got it right now? I think. Right? So I want to define a form downstairs. The lifts of these tangent things are not the same, but mu has to agree on it, on these two, right? And then, so you look at lambda 1 of v minus lambda 2 of v, right? Those are, in each case, k vectors. Number is k, it's a k form, so k vectors, right? Yeah. The difference of these has to be a k vector tangent to the fiber, right? You agree? The difference of these things has to be a k vector tangent to the fiber, because when you push them down, you have to get the same vector downstairs. This thing has to be a k vector tangent. Thank you, Deepak. The fiber. Okay? But condition 2 says that therefore condition 2 implies mu implies star. Okay. Because the contraction of any vector tangent to the fiber kills the form. Okay? We're not finished. That's the second point in your idea. You say lift and try to make sure they agree. The second point in your idea was, you forgot to say that, well, you probably had it in your head, that you could lift at another point. The two problems here, the well-definedness at one point and the lift at the other point. That's not a problem because of condition 1. So the form is invariant, and that's just the fiber of this principal bundle. So it agrees along the points, and so there's no point. So 2 implies star, and condition 1 implies can carry out, is independent of the choice of the point of the lift. So let's call this point here P, and the definition is independent of P. And the choice of P. Okay, the questions? First of all, I screwed up the notation, but you got me right on that now. I'm okay on the notation. Right? It's pretty obvious, right? Two different lifts differ by something in the fiber, so that's obvious, and then the invariance kicks on the two. Okay? Now, return to our example, to the Fubini-Studi setting. So, I'm glad that Deepak pointed that out. I start, the logic here is I start upstairs and check whether or not the conditions are fulfilled. Right? Yeah? So start, let's write the Fubini-Studi thing again right here. You're getting tired of me writing it. Right. So we start, this is pi, start with mu upstairs. Okay, and I'm going to give you the mu, which is my friend. I've talked about this several times. I love this mu. It is essentially the only mu you can use for certain purposes, in particular for the purpose of Kähler. You put this coefficient here in order to ensure reality of the form, and in order to make it invariant and trivial along the fiber, you have to take log. Okay? Now the invariance of this form is if you take an element of C star, G, in the structure group at hand, G star of all of this horrible thing equals all of this horrible thing, because G is holomorphic. It goes through a D and D bar, and it's simply then G star of the log norm, and the norm is invariant. So this is G star of mu. So that is condition, this is the invariance condition, that is condition 1. Okay? Okay, good. So I have an invariant form. That's what I was telling you. The problem with this darn thing, the norm function, if I dilate the norm function, well, let's say absolute value here, it dilates multiplicatively. And multiplicative change of coordinates is terrible, but additive is good because I can kill it with differentiation. That's what I just did. I take log, and then that changes by addition, and then differentiation kills that change. That's what happened. So that's good. And then finally, we need to check the non-degenerate. That is easy to check. So we check. In fact, what do I need to check? Well, I need to check that mu, the contraction of a vector is above with mu is 0, and where Vp is tangent to the fiber. Okay, and the fiber. So let's look at the fiber. The fiber is isomorphic to C star by taking something W in C star and goes to W times V. And now let's look at what happens to that function. So I'm looking at that function again. d bar of log norm W V squared equals I over 2 dV bar of absolute, log makes things additive, so this is log absolute W squared plus a constant, which is just log of norm V. That's a constant. And here's the variable, and dd bar of log norm is 0, because log norm is harmonic. So dd bar of log norm is 0, because the norm function in one variable is harmonic. The norm function is harmonic. The norm is harmonic. dD bar in one variable is the Laplacian. So it's a harmonic function. So this says that it's trivial along the fiber and gives us a form on the base. You look like you have a question.
So why did we split the product like that?
Well, the constant is just the norm of whatever vector you chose. And then I just fix a vector. So what is the fiber? Again, let's go through it again. The fiber is an orbit of the group. You fix it, okay, fix some point in the fiber. Take the orbit of that. So that's just a fixed vector. The orbit, of course, is multiplying by all elements of C star. Right?
Yes.
So what's varying in the fiber is really the C star, because I fixed that point. Okay? So now I take dd bar of that. The vector that I fix is fixed, is fixed, is fixed. So dd bar of it is 0.
Yes. Okay, yeah, but it's just, so in the computation, you say the logarithm of the norm W dot of the phi. Yeah.
You add the logarithm.
Okay.
You multiply the logarithm of the product. Log is a homomorphism from the multiplicative group to the additive.
Right, that's what there is to do.
Okay?
Yeah.
Okay. Great. It's clear, right? And so this is the condition. This is wonderful. So it pushes down. So omega Fubini Studi equals the push down. Of this form that I just told you about, I over 2 dd bar log norm squared. This number here is not too important, and I hope that I've gotten this positive definite and not negative definite. It's always a problem. So this is the push. And now what you have to check, and this is because I know complex analysis, but you can check it directly with brute force, is that this Fubini Studi form is positive definite. And of course, what that means is that the Hermitian form that we have here, the Hermitian Fubini-Studi form, which is equal to the Fubini-Studi metric minus I times the Fubini-Studi-Taylor form, it means that this thing is really a Riemannian metric. Now, you just have to check that. It's checking the positive definiteness of this thing. Okay? The various ways to check. Okay. Okay, that's wonderful. Yes?
Well, so you say you want to check the contraction of Vp under form mu is 0. So how does this, I mean, where do you check that? Why is it equivalent to checking
Well,
that?
I hope mu is upstairs. So I have the form upstairs, and I take a tangent vector to the fiber and contract mu.
Like, what is contracting mean?
Stick it into the first element. Or stick it into any element. You know, since the form's alternated, it doesn't matter. Right? It'll just be a sign difference.
I don't see how.
Okay, there's something missing here. The contraction with a vector field, or say vector, of any form omega is omega of the vector, and then the rest of the things run. So this pushes a form from a k form to a k minus 1 form. You just put it in somewhere.
What if there's no symmetry in the form?
What?
What if there is no symmetry in the form?
Well, the form is always an alternating form, so the only thing that's going to happen here is if I put it in at the third place or the second place, it's going to change the sign, right?
Right. So it's not, this notation is only for forms.
This is only for forms right now, anyway, yeah. Okay? Okay, this is the basic thing. Don't forget, the basic thing here is the Cartan lemma. D contraction plus contraction D is the derivative. So, I mean, that's what we're saying. Okay? So with almost 2 days of discussion, but I think it's been worth it, you've seen how we get a beautiful form on projective space. And please note that that SU n plus 1, which is contained in SL n plus 1, which is effectively the holomorphic automorphism group. I've talked about this in previous lectures. Effectively the holomorphic automorphism group of Pn. Okay? And in this picture here, this is again the picture I had yesterday when we were talking to Maria about this thing. Here's the picture. Here's 0. Here are all these lines going through 0. These are the equivalence class. Here's projective space. And the action of SU n plus 1 is upstairs, but it pushes down. So the picture you have is an SUN orbit upstairs. Looks like this. These are the SUN plus 1 orbits upstairs. And they act transitively on all the, SUN plus 1 acts transitively on the lines. I can map one line to another with the appropriate choice of SUN. So this actually pushes down also because the norm, this pushes down also because the norm is invariant. Pushes down to isometries the Fubini-Studi metric. Okay? Because the norm is invariant, and the Fubini and the SUN action preserves the norm. So not only do we push down to get a beautiful thing, since the norm is invariant, that means the group action leaves this thing invariant, and therefore it's defined at the level here. So we have a huge isometry group on thing. So this implies that there's an obvious map, which is almost an injection into the isometry group of Dn equipped with, maybe I'll put the metric here, Fubini-Study metric. Now you're probably going to ask a very good question here. If you're starting to ask good questions, you should ask, is this the whole isometry group, just the linear transformations? The answer is clearly no, because you have complex conjugation acting. But then the question is, except for something like complex conjugation, which is anti-holomorphic, do you have anything else? And that is, I think, well known, and but it requires a little work. So you might think about it, see if you can do it yourself if you're interested. So the question is, what is this isometry group of the Fubini-Study metric? Do you get much more than these linear isometries? Yeah. My claim is essentially nothing essentially more. Just complex conjugation or a little bit more. You might think about it. Okay. This is more or less an injection. The point is the center does not act. You see, you have the diagonal matrices. Okay, that's that. Now, why in the devil did I do this? Why bother? Well, I think projective space is interesting. This is my question, so I get to ask the question. Why bother? And the answer is immediate. The restriction of a calorimetric, a Kähler form or metric to a complex submanifold is Kähler. Check it. You just need to check it. Yeah. Let me tell you, if you're a pro, and we're starting to come to the level where I regard you as professional. If you're a professional and you see this situation, you say, okay, let X be a submanifold of Y, complex. Yeah. Then you say that the tangent bundle of X is a subbundle of the tangent bundle of Y. And J is acting on the tangent bundle of Y, and X is complex, so J stabilizes X, so therefore J stabilizes the tangent bundle of X. So that's the proof that if you have a J here doing the right thing, then you're going to have the J here doing the right thing. But the picture, you should complete this picture with the quotient. So if you have an injection of something here, then you have a quotient. And guess what you have? If you have X is here, and you have here all the tangent stuff in X, the quotient is the stuff that is normal. So the quotient is called the normal bundle of X in Y. Okay, so if that is the associated situation, obviously, and so that's very interesting. Yes, that's the definition of the normal. That was your question in some sense. You see, a normal, that's very important to see. Let's discuss that a little bit. That's the definition of the normal bundle. If you have a metric, then you can take the orthogonal complement. This discussion does not require a metric, right? Now you always have metrics, so you can take an orthogonal complement if you want, but that's a particular choice, right? It's this thing that if you learn bad linear algebra at first, you're in trouble. Yes? If I ask a student, here is a subspace, where's what is orthogonal to that subspace, the student will always write this. Right? And I say, what's your metric? And the student will not understand the question. And I say, my orthogonal complement is that, and the student goes completely crazy. Okay? There's no canonical orthogonal complement. That was a big point in some sense, right? We're defining here the normal bundle is just simply the quotient. And the quotient is well defined. The quotient of two vector spaces is well defined. That's no problem. Okay. Very good. So you see that algebraic geometry is contained in Kähler geometry, and Kähler geometry is a special kind of Riemannian geometry. Right? And the hookup is symplectic geometry. Okay, you can't separate these things. I love this picture, as you can see. Okay, that is one way of making examples. And now, other ways. Well, thanks for coming on this beautiful day. It's not obvious. It's really beautiful. I hope I don't ruin this beautiful day with trying to make beautiful remarks. So, a second method, but essentially same method. Same method. For constructing Riemannian metric. Okay. And let me call this tilde be a manifold. Of course, when I say that, I mean smooth manifold. The method I'm going to explain is exactly the same, but you've never thought of it. That's the reason I say essentially. You've never thought. And gamma, a group of diffeomorphisms. Well, let me just write it properly. Gamma, subgroup of diffeomorphisms of M. I hope you know, I think you know, the group of diffeomorphisms is astronomically huge. Right? So I'm going to take a subgroup which satisfies the following. 1. Gamma is discrete. Now, what in the devil does that mean? Well, what I mean is, it's a zero-dimensional Lie group. Okay? And if you recall, maybe, we didn't talk very much about this morning, but I know that you have some background in Lie groups. A Lie group is by definition paracompact. And that means it has countable topology. That means, well, implies that it has countable topology. Okay? So that means that this group is countable in number. Okay? It means in particular it's countable. Okay? 2, the gamma action on M is free and proper. Okay? Now, let me draw the picture. Here's the picture. Here are the orbits. The orbits are discrete. That is a point V, a point P here in this thing. And that is what we have here is the orbit of P. It's discrete. Well, the nearby fibers are also discrete. It looks like the same picture. And well, it is the same picture. It's locally trivial. You have a local section. You are used to calling this thing a Gauss cover. Gauss means free action. The covering space, it depends on your notation, may not have free action, but this is a Gauss cover, free action. Yes?
So when you say that gamma is discrete, and you say it was zero-dimensional Lie group, so I don't see how we would have a smooth structure in discrete.
It goes to a point.
It's the point.
It's as stupid as it gets.
The fibers are points. The fibers are zero-dimensional manifolds.
Okay.
I mean, yeah, it is. I'm glad you're a little confused. I purposely tried to confuse you. I'm tired of you. It's good. Yeah. What?
You drew lots of points.
Huh?
You drew lots of points.
But that's fine.
Yeah, that's the orbit.
The action of
It could be finite, I think. But it's not uncountable, and it's discrete. Because it's zero-dimensional and the action is proper. Right? That means you have a quotient. So this is upstairs. This is the mapping pi. And this is downstairs, which is upstairs. I purposely didn't call this P this time, but I could have called it P. It's the same thing. If you like, it's a principal bundle. This is P modulo the covering group. This is called a Gauss cover. The real word Gauss I use because the action is free. It's in general possible that you would have isotropy for covering. However, there's one very wonderful example which is automatically Gauss, and you know it from at least some course. The universal cover is Gauss. Yeah? The universal cover is a manifold. It is equipped with the action of a discrete group in this sense, a free and proper action of a discrete group, and the quotient is the original manifold. Yes?
Can you precisely define a Galois covering space?
I would define it now. A Gauss covering space is a covering space with covering group gamma, which is acting freely and automatically proper because the definition of a covering space is a proper action.
Because it's essentially what
Yeah. So I haven't, I mean, this is the, yeah. Let me just put it here. This will be, in fact, a statement about a certain Gauss group, but I always call this Gauss cover. Okay? Okay? So you know there, of course, coverings are not, but e.g. m tilde equal the universal cover. Okay. 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 Now, so let's take a theorem. And I think the only proof of this theorem is complex analysis. Every time I talk to a topologist, he says he doesn't know a proof. And the proof in complex analysis is heavy analysis using, depends how you do it, but using harmonic theory. If M is a simply connected two manifold. This is a jargon of in topology or differential topology. So dimension comes first: two manifold, n manifold, three manifold. Two manifold, simply connected, also connected, of course. Then M is diffeomorphic to either the plane R2 or the sphere S2. Incredible theorem. I purposely formulated this way because I wanted to confuse you. Because you all love complex analysis, I know. And you think of the uniformization theorem as saying that it's either the plane, the disk, the plane, complex plane, or the unit disk, or Riemann sphere. Huh? But the disk and the complex plane are diffeomorphic to these things, so they're really only two. Right? They're really only two. Now it's a question, I want to give you a little history. There's a wonderfully interesting, I don't know where the accent goes here, if somebody knows, a wonderfully interesting mathematician named Rado. Prove interesting theorems. He proved, I don't know, 1920 or something like this, that every topological surface two manifold. So, and the same thing as above, except no smooth, just topological. Yeah, just topological. Every topological two manifold has a PL structure. PL means it's triangulate. It's triangulate. Triangle really pieced together out of triangles. Okay? Locally finite and so on. You can define that easily. Okay?
What does that mean precisely?
Piecewise linear. So, oh yeah, you weren't here this morning. I mentioned this morning. So it means piecewise linear. So you really can make a puzzle of it means triangles. In this case, triangles. You can just a piecewise linear puzzle. And that PL means piecewise linear. Okay. And of course, you can smooth this. So this can be smooth. And this implies, if you look at it for a minute, every two-manifold in the above sense it has a unique a smooth structure. So we come, yes?
But the triangulation is not canonical, right? So why would the structure be unique?
Here we go again, yeah.
Also, the triangulation, like the PL structure is not canonical, right?
Not canonical, no.
And then how can then there be a unique smooth structure?
You can prove it. Okay? It's not hard, yeah.
In general, isn't, I mean, for a manifold, for any manifold, you have a unique maximal lattice, right? And that gives you a unique smooth structure.
Well, no, no, I don't have any smooth atlas a priori. A priori, I just have this triangle, this topological atlas. Right, you give me a manifold that's topological, that's what I mean by this. You give me a topological manifold. Locally, it's homeomorphic to domain in R2. That's all you, no transition, nothing about it. Okay, and I have to smooth this. Okay? Okay. This is always a the uniqueness, let me comment on uniqueness. She's worried, correctly so, about unique differentiable structures. And the place to start really worrying about it is on a sphere. Okay? And you have to think how you're going to make a sphere. I'm going to tell you how you make a sphere. You take what's this thing where you eat breakfast out of? A bowl. You take this bowl and you move it up, and now you have to put a cap on it. I'm doing what is called childlike Morse theory right now. So you put a cap on it, but the cap is going to be glued to the lid of the bowl. Yeah, you see, you put it, yeah? And this gluing has to be smooth somehow. So the boundary of the cap on the top has to be glued to the boundary of the cap on the bottom. Right? That's a diffeomorphism of S1, because the S1 is the unit circle where you're gluing. Okay? Okay. Fact, there's precisely one, there's no problem with this diffeomorphism, it's more or less unique. No problem. You can find it. Okay? So you're happy. I do it with S3. I take a bowl, I take a top, I take a gluing. The boundary is now not an S1, it's an S2. You look at you're gluing with diffeomorphisms of S2. There's no obstruction. You glue it. You go to S4, you do it again. You get to about S5, you can't do it. Because these two things where you're trying to glue will be incompatible. Okay? And this has been proved precisely. People saw this in the, I guess, 1950s. I always quote Milner on this argument. Very, very interesting fact that there's more than one differentiable structure as soon as you get to higher dimensions. Okay? On spheres, I think it's dimension 5. But in general, it's dimension 4. We talked about this maybe at lunch. There's no problem on dimension 2 and 3, but in dimension 4, there's a big time problem because they're not piecewise linear. That's one of the main problems in dimension 4. Okay? It's just something to keep in mind. It's fun to keep in mind. But Rado says that if you have a two-manifold, you've got a piecewise structure, you can smooth it. And you can prove that there's a unique smooth structure. It's not hard, and then there's a metric. G. Okay. Now, if you have, I'm just trying to convince you how deep all of this stuff is, giving you the history of this. Now, if you have a metric on a surface, on a smooth surface, that's very interesting. You have a metric on a smooth surface, which we will assume to be orientable, which is essentially no assumption whatsoever. I hope you know, if you have any manifold, there's always a 2-to-1 cover of that manifold which is orientable. There's a canonical 2-to-1 cover. Okay? You know that with the Möbius strip. There's a 2-to-1 cover of the Möbius strip, which is just a cylinder. So orientability is not really a problem. You can go to a cover, so we assume the manifold is orientable. We assume it's a surface. We assume it has a metric. Yeah. Well, good. Let's see what happens. Here's this manifold. It's a surface, and it has a metric. We take a point here, V. Why not this? JV. Well, now, I want a J. Right? All right, I hope I made propaganda for J's. What should be, this is surface. So that's the tangent space is a plane. So given a vector, you know precisely 2 vectors that are orthogonal and of the same length. You agree? Orthogonal with respect to that metric G. If the surface is orientable, we can take this thing to be orthogonal, the same length, and this be an oriented pair. Right? What? Take V. Rotation by 90 degrees is defined either minus or plus, I don't know which, but I define it to be in the oriented, positively oriented way. And now I have, of course, that. And so this implies that M is equipped with, and because this is an isometry, and omega tame, I can make omega from G, omega tame, complex, infinite, I'm going to emphasize, infinitesimal complex structure. On the tangent space, just rotation by 90 degrees. Okay. And now I think Gauss knew this. Certainly this was known around the time of Gauss. Theorem. In dimension 2, every such complex structure comes from a coordinates. So already here, you see Gromov's idea playing out. You should look at infinitesimal complex structure, but you're lucky. In dimension 2, if you don't believe me, check that the Nijenhuis tensor is automatically 0. But that's not the good proof. You can prove it independently. I don't know who proved this theorem. Probably even Gauss. I think maybe Gauss knew this. In dimension 2. Okay. This implies that M is a complex manifold. dimension 2. And it implies that the universal cover is biholomorphically equivalent this is what you were frowning about before, to either the disk, the plane, or the Riemann sphere. Okay. Very interesting, right? You start with the topological setup. Rado tells you, in fact, you've got a PL structure. You smooth it, you've got a smooth structure. You've got a smooth structure, you've got a metric. Rotation by 90 degrees works here, you don't have to think much. You've got an almost complex structure, an infinitesimal structure. Use the fact that, in fact, in dimension 2, there are coordinates. Therefore, this thing's a complex manifold. Therefore, you have the uniformization theorem. Okay? Time to stop. Let's meet again at 5:15. Is that okay?